Hi, everyone. We'll get started in a minute. Okay. What answers did you get for the first question? Okay, good. 5 is correct. Let's see. Neil, can you explain?
That wasn't actually Neil. That was me. Neil is not here for this one, but it wasn't that. Basically, you take the highest number, which is for 35 cents, is a quarter and a dime. That's 2 coins, and then for the highest number, it's 7 nickels. 7 minus 2 is 5.
Okay, good. Yeah, so this was an easier one. So we wanted to have a total of 35 cents. And what are the kind of choices and coins you can use? So for the smallest number of coins, you can use 1 25-cent coin or 1 quarter and 1 10-cent dime. Or kind of to use the maximum coins, you want to use the smallest one. So you can use a 5-cent coin, and you need 7 of these. So 7 nickels or a quarter and a dime. So the maximum is 7 coins, minimum is 2 coins. The difference is 5. Any questions on this? Okay, let's move to the second one. Okay, good. 728 is right. Nivi, can you explain?
Yeah, so I did like cases. So for it to be an even integer, the units digit has to be an even number, just saying that up front. So I first did the case where if the thousands digit was even, meaning that the digit was 4 or 6, which means there are 4 possibilities for the unit digit, 8 possibilities for the hundredth digit, 7 possibilities for the 10th digit. So you do 2 times 8 times 7 times oh my god, I can't read my work. Times,
No problem.
1 second, I'm just gonna
4.
4. Okay, sorry, I kind of did it in a rush. And then for when it's odd, the possibilities, the thousand digit would be 5, or so there would be 5 possibilities for the units digit, 8 possibilities for the hundredth digit, 7 possibilities for the 10th unit. 1 times 8 times 7 times 5 is 280. And then with those possibilities, you do 280 plus 448, and you get 728.
Good. Yeah. So this is correct. So yeah, like I think the important piece here is that first, you know that if it's between 4,000 and 7,000, it has to start with 4, 5, or 6, right? It has to be in the 4,000s, 5,000s, or 6,000s. So if it's one of between these kind of 3 choices of the first digit, you want to now see what are the choices for the remaining 3 digits, such that these 2 things are satisfied, right? It's an even integer, and it has 4 different digits. So for an even integer, we know that it has to end in 0, 2, 4, 6, or 8. Now, the kind of the issue that happens if we choose 4 or 6 versus 5, if we choose 5, of course, we can end with any of these digits, right? 0, 2, 4, 6, or 8. But if we chose to start with 4 or 6, we can't also end with 4 or 6, right? So we have to end with 0, 2, or 8, or whichever one of the 4 and 6 that we didn't actually use initially. So that's why we also need to split. We can't do any of the 3 choices for the first digit together. We have to split it into these 2, the even choices and the odd choices. So let's start with the even one. So with 4 and 6 is the first digit. So now instead of looking at the middle 2 digits first, let's look at the last digit now. So how many choices are there? So if I put 4 here, we can look at the last digit could be 0, 2, it could be 6, it could be 8, right? There's 4 choices. So you could even consider these separately, 4 and 6, or we'll see that they're actually the same. So that's the 2 here. And the 4 is going to be the 4 choices for the last digit. So we know that of the 10 digits, we've now used up 2 of them, right? So there's 8 digits left. So 8 choices for this digit and 1 less for the third digit. We know that all 4 need to be distinct. So this third digit has 7 choices instead of 8. So it's 8 times 7 for the middle 2 digits, 4 choices for the last digit, and 2 choices for the first digit. It can be 4 or 6. So if we multiply this out, we see it's 56 times 8, which is 448. Now let's look at the third case. So we've covered 4 and 6. Let's do 5. So 5 is the first digit. For the remaining digits, we know the last digit now can be any of 0, 2, 4, 6, or 8. So there's 5 choices for the last digit. Now the same approach for the middle 2 digits. We've used up 2 possible digits. So there's now 8 digits to choose from for the second digit. And once we put 1 for that, now there's only 7 numbers left to put in this position, since we again need to have them all distinct. So 8 times 7 to fill these 2, 5 choices for the last one. So 8 times 7 times 5, we know is 280. So 280 plus 448 gives us the answer of 728. Any questions on this? Okay, let's move to the last one. Any ideas on this one? Okay, let's go over it. Okay, so we know this, a natural number is nice if it's equal to the product of its distinct proper divisors. Now, proper divisors are all the divisors except for 1 and the number itself. So let's take an example, and let's take the number 12. What are its divisors?
Its divisors itself would be 1, 2, 3, 4, 6, and then 12, yes.
Okay, good. What are its proper divisors?
2, 3, 4, and 6.
Good. Okay, so divisors of 12 are these. Proper divisors is just remove 1 in itself, right? So that's kind of, once you see that, okay, proper divisors is just removing 1 and the number itself. Okay, so now we want to say a number is nice if the product of its distinct proper divisors, so of course the different, so all the different proper divisors, is equal to the number itself. So what is the product of the proper divisors here?
$144.
Good. So is this number a nice number?
No.
No, right? Because we know that the number would be a proper, so the number is nice only if the product of its distinct proper divisors is equal to the number itself, right? So we wanted this number to be 12. So let's pick a different number. Just to try it out, let's take the number 14. Sorry. What are its divisors?
1, 2, 7, 14.
Good. What are its proper divisors?
2 and 7.
Okay. And what's that product?
It's 14, meaning that it's a nice number.
Good. Does this help figure out what are the cases when we have a nice number? Okay, let's think about this another way. When I list out all the proper divisors in order, right? So this is in both these cases, we've done that, right? 2, 3, 4, 6, 2, 7. What do I always know about multiplying the smallest one and the largest one?
It's going to equal the number that
Good.
the divisors are from.
Why is that?
Because, well, if you multiply any two numbers on, so it would be 3 and 4, 2 and 6, and then 1 and 12 on the upper chart. It's just how you multiply them out.
Good, yeah. So any divisor, basically when you divide it by the number, there's like some quotient, right? So both of the number and the kind of what it multiplies, both are divisors, right? So if I pick kind of the smallest number to multiply, to divide out, it leaves you the largest divisor, right? So if you think about these proper divisors, I can pair them up, right? So 2 and 6 will multiply to 12, 3 and 4 will multiply to 12, and so on. So in this case, 2 and 7 multiply to 14. And this is true even if I had 20 divisors here. The first and last would multiply to the number. The second and the 19th would multiply to the number, and so on. Okay, so can you now tell me some kind of criteria on the proper divisors that will make it nice? What should be true here?
There should only be 4 divisors or 4 divisors or 2 proper divisors.
Good. So a number is nice if it has 4 divisors, or which is equivalent to 2 proper divisors, or 2 proper divisors. So yeah, so we know that now proper divisors, you're just removing 1 in the number itself, right? So basically you're subtracting 2 from the number of divisors. So if a number has 2 proper divisors, and we saw one example up here, 2 and 7, when you are the proper divisors, multiplying that gives you 14. 14 itself has 4 divisors and 2 proper divisors. Okay, so effectively this question is asking us, what is the sum of the 5 numbers, the first 5 numbers with 4 divisors? Okay, so now there's 2 ways of approaching this. One is we can start thinking of numbers with 4 divisors, and then we can look at kind of a more formulaic way of thinking about it. But let's start with the first way. So give me some small numbers with 4 divisors.
8.
6 and 8.
Good, 6 and 8. So 6, what are 6's divisors?
1, 2, 3, and 6.
Good. 8?
1, 2, 4.
Good. What else?
10.
Good. What are its divisors?
1, 2, 5, and 10.
What else?
14.
Good.
1, 2, 7, 14.
Good. What else?
22.
Okay.
1, 2, 11, and 22.
Okay. Anything else before 20?
Isn't there 18?
Good.
But that has 3 and 6.
Yeah.
Oh, okay.
Anything else here?
Isn't that all we need? Because it says first 5.
It could be, unless there's something smaller than 22.
15.
Good. Why 15?
1, 3, 5, 15.
Good. Okay. Can anyone think of anything smaller than any of the numbers we have here? Okay, so I agree there isn't. So what would the answer be now?
$43.
Close.
53.
Good, 53. So it's 6 plus 8 plus 10 plus 14 plus 15, right? So let's add these up. So 15 plus 14 is 29, plus 10, 39, plus 8 is 47, plus 6 is 53. So 53 is the answer. That's good. And we found the 5 numbers. So we know that these 5 smallest numbers, and we could check now. We saw we have all the divisors, right? So 6's divisors are 1, 2, 3, 6. Proper divisors are just 2 and 3. 2 times 3 is 6. 8, proper divisors are 2 and 4. Product is 8, matches up. 10, 2 and 5, product is 10, matches, and so on, right? We see 14, 15, and we can double check that. Okay, so now instead, it kind of took a while, or you might have missed that 22 was larger and taken that instead of 15. So what is another way of doing this where we can kind of be sure that we have the smallest 5 numbers? Any ideas?
Look at all of it. You can do like as multiples of like 2, 3, 2, 4, 2, 5, 2, 6, and then 2, 7, but 2, 6 doesn't work, and then work up until with all the single digit numbers, and then 3, 2, 3, kind of like that. Does that make sense?
Yeah, I think that's the right approach. But so what is the, so we know this property, right? So the number is nice if it has 4 divisors. What is the kind of formulaic way of finding the number of divisors for a number? So if I give you any number, how do you figure out the number of divisors it has?
Prime factorization.
Okay, and what do you do after you have the prime factorization?
Then you like add 1 to each of like the exponents and then find the product of that. So something like that.
Yeah, that's good. That's correct. So you take the prime factorization of the number. So let's say it's like 2 to the power of something times 3 to the power of something is an example of the prime factorization. So if you take those powers, let's say they're A and B, add 1 to each of them. And if there could be more than 2, I'm just giving you an example with 2, and then you multiply these together. And that gives you the total number of divisors. Okay, so if I know that the number of divisors needs to be 4, what could I have multiplied to get 4? So I want this number to be 4 here.
A and B are 1, or
Okay.
Oh yeah.
Or anything else?
Well, A could be 2, and then wait, no.
What if A is 3? So another way to think about this is, what if we only had 1?
0.
Good. Yeah. So these are 2 of them. So we actually don't need to be limited by 2 numbers. We could even imagine this as 2 to the power something times 3 to the power something times 5 to the power something. But we'll see that doesn't actually give us anything better, because you can actually divide 4 into the product of 3 different things that are not 1, right? So actually, these are the only 2 cases. So what does this actually mean? So I didn't even care about the bases here, right? I'm only looking at the exponents, right? So when I'm saying A is 1 and B is 1, I'm saying the prime factorization is the product of 2 distinct prime numbers. Basically, there's 2 different prime numbers in the prime factorization, each of them to the power 1. What am I saying in the second case? What should be true?
One singular numbers can be multiplied to find the product.
Good. So one single prime number taken to what exponent?
To 1, to the power of the exponent of 1.
So here we've said A is 3 here, right? So in this case, if we had A is 3, so B is 0, that just kind of goes away, right? So it's just some 2 to the power 3 is an example, right? When A is 3 and B is 0, right? Alternatively, it could be something like 3 to the 3 or 5 to the 3. So in this way, it's just the cube of a prime number. Does that make sense?
Sorry, can you say that again? Sorry.
Sure. Yeah, so basically the idea, what we're trying to do here is looking at what prime factorizations will lead to a number with 4 divisors, right? So one way is it could be some prime number p to the power 1 times q to the power 1. So we know from this kind of method of finding out the number of factors, once I have the prime factorization, I look at each exponent, add 1, and multiply them. So if there's 2 with 1s, 1 plus 1 is 2, 1 plus 1 is 2, and I multiply that to 4. So this is one way of kind of getting 4, but there's another way, which is just a single prime number to the power 3. And that was what we found before as a is equal to 3, b equals 0, right? In this case, when we look at the prime factorization being some prime to the power 3, if we add 1 to each exponent, if there's only one exponent here, it's 3, add 1 to it is 4, there's nothing to multiply because there's only one exponent here. So this is another kind of pattern of the prime factorization that might lead to 4 divisors. But what is a prime? Okay, so basically what this means is there's one prime factor to the raised to the power 3. So basically this occurs when the number is the cube of a prime number. Does that make sense?
Yeah, sorry, it just hit me. Sorry.
No
Yeah, I
problem.
understand. Thank you.
Okay, good. Okay, so now we kind of know the template of these numbers, right? So either the numbers that we're looking for, or all these nice numbers, are either going to be product of 2 prime numbers or the cube of a prime number. So what are the smallest prime numbers in order? Or let's limit it to 5. What are the first 5 prime numbers?
1, 3, 5.
2, 3,
Oh,
5,
Good. 2, 3, 5.
7, and 11.
Good. Yeah. 2, 3, 5, 7, 11. Okay. So now we know it's in these 2 patterns, right? Okay. So let's look at product of 2 prime numbers. What are the smallest ones there? And let's actually
2
write
and
it.
3.
So what are the possible choices here? So it's 2 times 3 is the smallest one, of course. What is next?
3 and 5. Oh yeah, 2.
2 times
5.
5. Okay. What else?
2 times 7.
Good. Then
And then 3 times 5.
good. What's next?
2 times 11.
Good.
And,
The 3 times 7 is actually smaller, but yeah.
oh,
2
3
times
times 7. Then 2 times 11. And then
Okay, we can stop there. So that's on the product of 2 prime numbers. And what about the cubes of prime numbers? What are the smallest ones there?
8's the smallest.
8's the smallest, yep. And what's the next one?
27.
Good, that's 3 to the 3rd, right?
Yes.
So this is 8 and 27. Okay, so now we know these are the smallest in each of the categories, right? So now let's combine them to get what are the 5 smallest overall. So 6 is here in the first list, then 8 is there in the second list, then 10 in the first one, then 14 in the first one, and then 15 in the first list. So we won't get to 27 because there are smaller ones in the first list. So now we know for sure that we have the 5 smallest ones because we know it has to be either the product of 2 distinct prime numbers or the cube of a prime number. We looked at the first smallest prime numbers and found all the numbers that fit that, the smallest ones, and the smallest ones that fit the cube criteria, and then combined these 2 to find the 5 smallest overall. And those are the same 5 that we found initially thinking about divisors. And we'd of course get the same sum here of 53. Any questions on this? Okay, then that's it for today's class.
Thank you. Thank
you.
Happy
Thank
Ugadi.
you.
Happy Ugadi.
You got the-
You.